Hello, I'm Daniel Woods. I'm a postdoc at the University of Innsbruck in the Austrian Alps. And today I will be presenting our systemization of knowledge about quantifying cyber risk. So to use your time efficiently, we split our talk into two sections. The first part is a tutorial on our causal model of cyber risk, which we later used to systematize the literature. The second section explains what we learned from our survey of empirical cyber risk papers. So, in trying to explain the causal role of security interventions, a natural law might go something like, the more security an entity has, the less harm they will suffer. This is almost true by definition, and we can describe this visually with the negative sign denoting a negative relationship. Namely, more security leads to less harm. Yet, in the literature, we find results with the opposite relationship. For example, Zen and Borla find that higher security budgets are associated with higher frequency of data breaches. So this seems to contradict our natural law, but we can explain this result via confounding variables. So we illustrate this with artificial data showing the same results. The line of best fit shows that entities who invest more in security tend to also suffer more harm. So we don't believe it's the case that security investments cause greater harm. Rather, we think entities who anticipate more harm will also invest more in security. Such entities face a higher threat level, and we use this term to capture the motivation, capability, and activity of adversaries. So, separating these observations by threat levels illustrates this. Entities with higher threat level, which we depict in red, tend to invest more in security than entities with a lower threat level. Now, if we fit a separate line of best fit for the high threat population, we see the result we expect. More security is associated with less harm. This suggests a statistical model of cyber risk outcomes should include variables in addition to security. This follows because an active threat actor is the only necessary condition for harm to occur. Thus, the cause of harm is the threat actor, not the security level. So, the backbone of our model should be a positive relationship between threat level and harm, which can be seen here. However, all hope is not lost. Interventions exist that can reduce expected harm for a given threat level, and we call the sum of all such interventions the security level. Here we have the expected relationship. For a given threat level, a higher security level leads to less harm. In this sense, security moderates the relationship between harm and the threat level. There are also interventions that can increase expected harm. An example of such an intervention is retaining more personal data of customers or potentially giving more employees administrative credentials. We call the sum of all such interventions the exposure level. And here we have again a positive relationship in which more exposure is associated with more expected harm for any non-zero threat level. So, this is a great model in theory, but it faces two practical problems. First, these variables are difficult to measure, and second, few studies include all of the variables. So we now describe how we extend this basic model to address these concerns. So first, the measurement problem. Intuitively, we know that implementing security controls improves the security level. Thus, the seductive approach to measuring security is to enumerate, observe, and aggregate all controls that cause lower harm for a given threat level. Unfortunately, it is impractical to measure all such controls, not least because they're constantly changing. We argue instead it's better to think of each control as an indicator of an unobserved security level. Thus, more secure organizations are more likely to implement each control. So, a given control provides information about the overall security level, regardless of its causal impact. For example, two-factor authentication does not mitigate web vulnerabilities. However, organizations who implement two-factor authentication are also likely to conduct more rigorous code review that reduces the likelihood of web compromise. Clearly, such relationships are noisy. A given security control may be implemented by an insecure organization while also not being implemented by an otherwise secure organization. This statistical noise can be overcome by making many measurements and aggregating the results. The more measurements, the better. In the language of structural equation modeling, the measurement of each control is a reflexive indicator of the latent variable, namely the security level. This provides a pragmatic way of measuring organizational security without needing to observe every control. So the second practical problem with the simple model is that very few studies collect both indicators of preventative security and also indicators of harm, let alone linking the two statistically. So mitigation studies focus on preventative security, which covers interventions like, for example, patch management. Typical studies of preventative security link it to indicators of compromise like botnet infections, compromised web servers, or whether a data breach occurs. But this ignores harm outcomes like the dollar cost of a cyber incident. This is why, in this model, we replace the harm variable with a compromise variable. So, turning to cyber harm studies, we find that these studies try to quantify how harm varies among a population of compromised firms. Indicators of harm include the number of records lost in a data breach or the loss in shareholder value following a cyber incident. Such designs can say nothing about preventative security because they only sample firms where compromise is equal to 1. So we have two types of studies, one with compromise as the outcome variable and the other with compromise as an input variable. Thus, it makes sense to add compromise as an intermediate variable to our model. This essentially splits security in two. There are those interventions that happen before compromise and those incidents that happen after compromise, which we call preventative and reactive security, respectively. So, in the same way, we can also differentiate between the role of exposure before an incident and also after an incident. So, surface exposure relates to attack vectors used to achieve compromise, such as the number of accounts with administrative privileges, whereas asset exposure relates to factors amplifying harm resulting from a compromise, such as the volume of personal data of customers retained. So this full diagram is our causal model, and so far we have only provided a normative contribution explaining how we think the research community should quantify cyber risk. So the next part of our talk outlines what we learned from the literature. So we do the typical SoK thing with circles and semicircles by classifying each study according to which arms of the causal model were investigated. So for example here, the first 3 studies evaluated the impact of notifying system owners about vulnerabilities, but they did not link this to harm or compromise outcomes. Whereas the other 2 studies explored all 3 variables impacting the chosen proxies for compromise. So our full paper contained many more classifications, but given the time constraints here, we thought it would be more useful to show the audience what we learned from the harm studies, as we believe you're less likely to be aware of this work. So the harm studies tended to be published at econ and finance venues, and they also had a much longer sample window, which you can see in the final column. So the most common study type quantified stock market reactions to cyber incidents, which is an indicator of harm. And we conducted a meta-review of such studies. So this figure shows the size of the market reaction on the y-axis. So a negative value is bad for the victim firms. And we also show the sample window on the x-axis. So studies of events from before 2005 found evidence of more severe negative reactions. However, this effect was less pronounced in sample windows, including post-2005 incidents. Some of the authors of these studies suggest that this is because corporate officers learned how to release positive news alongside data breach announcements, while other authors report evidence of insider trading. So this highlights a challenge with measuring cyber risk. As soon as a measure, like stock market value, becomes meaningful, entities adapt behavior to optimize the metric. A separate question we should ask is whether there's a meaningful difference between a finding of minus 0.03 and minus 2.4. Would this meaningfully change how organizations manage cyber risk? So a simple razor we can use is statistical significance. More than half of the tests fail to reject the null hypothesis at the 5% significance level. Therefore, we suggest that these questions essentially struggle to answer the yes-no question: do cyber incidents lead to shareholder harm? So, the second most popular type of study was analyzing data breach events aggravated in public repositories. But rather than uncover longitudinal trends, additional data breach studies, which can be seen as a form of replication, actually created contradictions. So the first data breach study found that the frequency of data breaches was increasing over time. The second confirmed this and added the result that breach size was stable over time. Now, the third introduced the first contradiction. The third data breach study found that breach frequency is stable over time. And the fourth finds that breach size is increasing over time. The fifth, that breach frequency is actually decreasing over time. So we hope you can see the picture that's building up here. Additional studies don't confirm results. Rather, the application of more sophisticated methods led to differing and often contradictory results. So, we could not conduct a comparable meta-review for mitigation studies because they tended to analyze very different phenomena. Therefore, we struggled to distill any actionable insights for decision makers in terms of improving security decisions. This is partly because organizations are complex systems, and it's often easier to get data about the subcomponents. So for example, a great Usenix 2015 paper studied which websites would turn malicious using a sample of 5 million websites, and it collected historic features via the Internet Time Machine. A different study of web server compromise used a sample of 200,000 web servers. A study of web hosting providers used a sample of 45,000, and this was even smaller for a study of end-user device compromise, which had a sample size of 15,000. So, a study of malicious data breaches used a sample of just 600 observations, despite the fact that organizations are mandated by law, at least in the US, to reveal such breaches. And this sample size fell to 265 breaches when a study restricted this to breaches with a $1 loss. Notably, this study relied on a proprietary dataset created by a company who crawl all public reports of data breaches, and yet they only found 265 data breaches that publicly report the financial cost. So, in conclusion, we set about trying to understand the state of the art in quantifying cyber risk. Yet, 30 years of research has struggled to even identify the effect and causal direction of security. We started this talk with a spurious result in which the causal effect of security was flipped. we showed that stock market reactions often fail to establish statistical significance, and that data breach studies often contradict each other in terms of relatively basic questions about whether data breaches over time are increasing or decreasing in frequency or size. So, our interpretation of the literature is that these failures to establish knowledge are rooted in two problems: omitted explanatory variables that are compounded by a lack of observations. So, going forward, we hope that our causal model helps the community to organize assumptions and efficiently uncover signal in the noise. So, we thank you very much for watching this talk.